by Ana Villaconsejo and Tristan Salz. And feel free to start, Loki, whenever you're ready.
All right, thank you. So I was researching the influence of coral reef spur and groove morphology on wave attenuation. And I like to begin the presentation with this nice example. So this is the town of Chopu in Tahiti. There's a small township here. You can see a barrier reef around it and the white water indicating quite large waves that break on the barrier reef. This is the size of the waves that break on that reef. It's quite a famous surfing break, and you can see there's a large amount of wave energy here, which is dissipated on that reef and by the lagoon before it reaches the town of Chopu. This is what the reef looks like. The wave energy is dissipated by both wave breaking and bottom friction across the forereef, reef flat, and reef crest, which are the morphological zones of the reef that you can see here. There's also visible in this photo these key morphological features, spurs and grooves, the grooves being these indents and the spurs, the reef between them. So this isn't unique to Chopu. 200 million people globally receive this kind of protection from coral reefs, which has been studied in greater detail on the reef flat and the reef crest than the highly exposed forereef slope. The dissipation in this zone is largely due to the complex geometries of the forereef. And one of these key features that adds to the complexity of the geometry are these spurs and grooves. So these are prevalent across reefs globally, Caribbean, and the Great Barrier Reef. And the size, spacing, and alignment of these features has been observed to be tuned to the oncoming wave energy. So that leaves us with two research questions. Can we infer from a wave transformation simulation the effects of spurs and grooves on wave energy dissipation? And secondly, can we combine the impacts of loss of structural complexity and climate change to quantify the loss of coral reefs' capacity to dissipate wave energy? So how is this going to change in the future under climate change? So I'll step through from here the methods more for me. So then we used 0.5 meter resolution LiDAR bathymetry to conduct a quantitative geomorphic analysis to understand the relationships between spur and groove morphology and wave transformation. Next, we combined a number of other data sets, including satellite altimetry data, access from RadWave, climate change outcomes from the literature, and a relative wave exposure model known as GREMO to produce wave transformation models in XBeach to understand how wave energy is dissipated across spurs and grooves. Our study site was One Tree Reef. It's a lagoonal reef in the southern Capricorn, on the southern Great Barrier Reef in the Capricorn Bunker Group. One Tree Reef is a mature lagoonal reef with a semi-diurnal tide of 3 meters. And a number of sites were selected around the reef for this study, which reflect the range of spur and groove morphological arrangements and wave exposure. The site was also selected due to the availability of high-resolution LiDAR data. The 3D rendering here in the bottom left shows that it's of sufficient resolution to pick up these spur and groove features. So the quantitative geomorphic analysis looked at groove length, depth, width, direction, and sinuosity. And in doing so, we noticed that there is this alongshore sinusoidal pattern to the spurs and grooves, which allowed us to apply a fast Fourier transform, which is typically used in oceanographic studies to unpack wave climate. However, here we applied across a spatial scale rather than a temporal domain. And from that, we can extract the spur and groove spacing and the frequency that spacing occurs in a way that has potential to be scaled up to analyze entire reef systems. And this data was used to inform our analysis of wave transformation results. So we can see here the spectral density peaks indicate the Spur groove wavelength. So this data was input into XBeach. XBeach is an open source numerical model designed to simulate hydrodynamic and morphological processes on sandy coastlines. And recently there's been extensive validation of the model over the complex geometries of coral reefs. These are the bathymetries that were input into the models. So they reflect a range of wave energy exposure, but also a range of spur and groove morphologies as classified by Deuce et al. 2016. So we see that at site ON, the least protected, we get these long and short protected grooves. At site OS, all of the grooves are highly exposed to wave energy. And at site OE, we have both exposed to wave energy grooves and also deep and disconnected grooves, which are relic grooves that formed during the Holocene transgression. And these allow us to infer coral cover and understand reef platform evolution. Data was extracted of the wave climate from satellites that passed over the eastern side of One Tree Island so we could get the offshore wave height before the waves began to interact with the Great Barrier Reef matrix. And we extracted about 30 years of wave data. Here's a subsection of that. We see that the maximum wave height was 4.7 meters and a mean wave height of 1.3 meters. And there's a lot of other wave data that was input into the wave models there as well. But not all of the reef is exposed to the offshore wave height. So we incorporated a Gremo wave model as well to sort of synthesize the effects of refraction and reflection around the coral reef matrix. So in the models, we were able to compare to smooth bathymetries. And we see effects like this where there's high dissipation due to bed friction across the spurs compared to a smooth model where we don't see dissipation due to bed friction. So when the spurs and grooves are present, you see an increase in total wave energy dissipation and a decrease in wave energy dissipation due to breaking, as a lot of the energy is extracted due to bed friction. We also found in comparing different sites around the reef that longer spurs and grooves produce a longer dissipative zone as the dissipation due to bed friction occurs across the length of the spur. Where the spurs are shorter, we see a shorter dissipative zone with a greater contribution of wave energy dissipation from wave breaking. So in forecasting into the future, we had to consider a number of different climate change effects, namely sea level rise, both static and relative, which is dominated by the accretion and the erosion of the reef. We see an increase in wave power and also a loss of bed friction, the latter of which was one of the most influential on wave energy dissipation. So loss of bed friction is due to the loss of coral cover, a loss of structural complexity. And these images here from a paper from 2007 show the change in reef structural complexity given changes in atmospheric CO2 and sea surface temperature. So when this was produced in 2007, the CO2 concentration was at 380, closest to this image here. And as of yesterday, it's closer to 420 parts per million as measured at Manualoa, Hawaii. And this is input into the model based on a bed friction factor here, which is 0.9 for a healthy reef, very high, and 0.01 for an eroded rubble bed, such as in image C here. One of the key impacts that was observed was wave overtopping or overwash, which can be observed here. Also in this image, you can get an idea of the number of variables that will impact overwash. So this is influenced by the vertical accretion of coral reef islands and erosion rates as well. And we found that wave overtopping increases exponentially for worsening climate change outcomes, So we have present day RCP 2.6, 8.5, and a total disaster scenario of which we saw a maximum overtopping of 4 meters. This is likely to be greater if we consider run-up and tidal effects as well. And for example, 3.7 meters of overtopping at Roy Namur led to significant inland flooding. We also see a shift in the mode of wave energy dissipation from bed friction, shown here in orange, to wave breaking here in orange, and bed friction decreasing here in blue as we increase the climate change effects. And this is true across all of the wave models, with the exception of this one. So this graph here represents the bed profile. In blue is the dissipation, and in orange, the dissipation due to bed friction. You see decreasing with increasing climate change, except for RCP 8.5 here, where we see an increase in the total wave energy dissipation in blue. And that's brought about by this morphological feature here, the steep bathymetric incline, which induces wave breaking. So this feature is due to the sinuosity of spurs of the grooves. None of the grooves are straight, and as they bend, they create these steep bathymetric inclines shown here, which induces wave breaking. So some of the general trends that we see with an increase in sea level rise and a loss of reef structural complexity is the decrease in dissipation by bed friction, an exponential increase in wave overtopping. Dissipation by wave breaking increases until the water level is too high and the wave base no longer interacts with the reef bed, and it begins to rapidly decline after that threshold. So this leads to some negative outcomes for corals. Dissipation due to wave breaking. Corals that aren't exposed to wave energy in the past have a lower mechanical strength. And that's a frequent bleaching event. So we see increased coral breakage and reef erosion due to this increased wave breaking mode of dissipation. There's some potential positive outcomes. And we know that deeper grooves facilitate wave energy dissipation. So this erosion dissipation feedback loop may increase wave energy dissipation in the future. However, this is dependent on maintaining the environmental conditions that allow the spur lateral and vertical growth into the future. So some conclusions: can we infer from a wave transformation simulation the effects of spurs and grooves on wave energy dissipation? Yes. Long spurs and deep grooves facilitate wave energy dissipation by increasing bed friction on spurs, allowing onshore, offshore water flow, and we know that groove sinuosity induces wave breaking. Secondly, how is this going to change in the future with loss of structural complexity and climate change? A loss of bed friction typically results in increased dissipation due to breaking and decreased total wave energy dissipation, which resulted in the increased run-up that we saw in the previous models. We also found that increased reef erosion may promote the development of grooves, leading to increased wave energy dissipation in the future. Thank you very much.